Good morning. Day 2 of our video lessons. Yesterday's lesson was a little long, so I'm going to try and shorten ours today. In fact, I'm going to be doing more like 3 separate videos, just that you guys can stop at a certain point and come back and watch another video if you need to. So we're going to kind of break up this lesson a little bit and hopefully speed it up. So yesterday's lesson, I realized, might have seemed a little confusing. We did a couple tests that were more review style, and then all of a sudden I threw in a brand new type of test, and I just started going for it, and you're probably thinking, what is she doing? So we're going to back up a little bit and go over some of the basics of that second test, and then we're going to do a couple more today so you guys can kind of see how they're supposed to work. And you guys can always go back onto the Skittles example after we've done today and try it out on the Skittles example. So today you do have homework. It's going to be over here, and it's on the Chi Square Goodness of Fit test that I started to introduce to you yesterday. So just a reminder, we started with normal distributions. Normal distributions were used for your first set of tests. One proportion z-test and a 2 proportion z-test. Those are the last 2 chapters that we did, whether you were just testing one claimed proportion or you were testing between 2 proportions, which one was greater than. But with both of those, with proportions, we use the normal distribution. But I also taught you t-distributions, and t-distributions were also used for tests. A 1 sample t-test and a 2 sample t-test for means. So remember, with proportions we use a normal distribution with z-scores, and with means we use a t-distribution with t-scores, and we have to know our degrees of freedom. The third one we're going to be learning is the Chi Square Goodness of Fit. And yes, I said chi, not chai, it's chi. It's a Greek pronunciation of a Greek letter. So here's the symbol for it. That's chi. It's like a squiggly X. But we actually call it chi squared. So the tests that we're going to be using a chi squared distribution on is 3 different types of tests. Chi squared goodness of fit, chi squared homogeneity, and chi squared independence. Okay, thankfully, homogeneity and independence are practically the same test. The only difference is how you write your null and alternative hypothesis. So goodness of fit's a little bit different, and so that's where we're going to start. Now, yesterday you may have noticed that I drew a picture a little bit differently. You know how I love my pictures. I think they're super helpful. So whenever you get to the do portion of a 4-step process, you're going to need to draw your picture. But this distribution is not normal. It looks a little something like that. What do you notice about that distribution? Hopefully you're saying that it is skewed to the right. That is your chi squared distribution. And yes, it is skewed to the right. And it's no longer a normal distribution. We're going to be using a completely new distribution. So let me tell you a little bit about these chi-squared distributions. The chi-squared distributions are a family of distributions that take on only positive values. Hopefully you guys noticed that I drew this vertical line here, which is basically like a y-axis. It's starting at the very beginning, at the origin, which is 0. So it takes on only positive values. There's not going to be any negative values like negative z-scores on a normal distribution. That's just not going to happen in a chi-squared distribution. All chi-squared distributions are skewed to the right. None of them will be skewed to the left. They're all going to look like this. Now, some might be more skewed than the others, but they're all going to be skewed to the right. A specific chi-squared distribution is specified by one parameter called the degrees of freedom. You guys are familiar with the degrees of freedom, and we're also going to deal with those with chi squared. Degrees of freedom is equal to n minus 1 like you're used to, except n is no longer our sample size here. N is going to be the number of categories. So think back to yesterday's lesson when we did the Skittles example. The Skittles example had 5 categories. It was each of the different colors, red, orange, yellow, green, purple. That would be the 5 categories. So on a chi-square distribution yesterday with Skittles, it'd be 5 minus 1, a degrees of freedom of 4. Okay, so a few more things that we want to know about a chi-square distribution is the area under the chi-square curve is equal to 1. Hopefully you guessed that. It's still a density curve. All density curves have an area under the curve of 1. Each chi-square curve begins at 0, like I mentioned above. They increase to a peak and then approach the horizontal axis asymptotically from above. They all head upwards and then come down and then get closer and closer and closer to that x-axis, but never actually cross it. That's the asymptotically that it's talking about. As the degrees of freedom increase, so as you get more and more categories, the distribution becomes more normal. You kind of saw that with the t distribution as well. As the degrees of freedom increased, the t distribution became more normal. So what ends up happening is that curve gets closer and closer to more of a normal standard, not so much as skewed. And that's because the mean of a particular chi-square distribution is equal to the degrees of freedom. So as the degrees of freedom increase, the mean increases. And then the mode of the chi-square density curve is always at degrees of freedom minus 2. Okay, we don't need to get into that too much, but so as these get larger, they seem to get closer and closer together, which is what makes it more normal looking as the degrees of freedom increase. Okay, so those are just a few things to know about a chi-square distribution. Now, whenever we're about to use a chi-square distribution, we have to remember to check our conditions, just like we always do in all the 4-step processes and any kind of significance test or confidence interval. So we have our 2 typical conditions. Random, you guys are familiar with that one. The data must come from a random sample or a randomized experiment. Okay, and again, anytime we take our random sample, if it's some kind of SRS, we need to do the 10% condition because that's when we are sampling without replacement. Okay, so whenever we're sampling without replacement, we have to check that n is less than or equal to 1/10 n. Okay, that their sample size is less than 10% of the population. And then, of course, normally for the second condition, it's the normal condition, but we're actually changing it to the large sample size condition because we're not using a normal distribution. So we're not going to check for a normal condition. Instead, we just need to make sure that the sample size is large enough. So it's actually a pretty basic concept. All the expected counts, and we'll get into what an expected count is, but all the expected counts are at least 5. Okay, so a couple warnings about that last condition especially. The chi-squared test statistic compares the observed and expected counts. You noticed yesterday that we didn't use the percentages, we used how many Skittles. So how many Skittles of each color did you get, and then we compared it to how many Skittles we would have expected out of that sample. So we used the counts, not the percentages like we're used to. When we're checking the large sample size condition, be sure to look at the expected counts and not the observed counts. So again, when we're checking this condition, we want it to be expected counts. Not what we actually got in the sample, but what we would be expecting to get. Okay, so I'm going to go ahead and stop my video here as the first part of the lesson. Go to the next video for the next example.